Hello, welcome back, children. Quick revision chapter is alternating current, AC. So we begin with the AC through resistor only circuit for quick revision. AC through resistor. AC when allowed to flow through resistor only circuit. R only. The resistance R alone is connected in an AC circuit. AC voltage supplied is V is equal to Vm sin omega t, where Vm is the voltage amplitude and V is the instantaneous voltage. Omega is the angular frequency of AC voltage supply. Then the equation for current is Im sin omega t, which makes it clear that the phase angle between voltage and current is to be 0, where Im is equal to Vm divided by R, where R is the resistance. Here it is also important to know the voltage and current versus time graph. Voltage, current, time graph. So voltage when plotted against time, you get a sine curve with peaks, voltage peaks at periodic intervals of times, and the peak value is Vm. And this would be the shape of the graph. Voltage becomes maximum and minimum periodically. Repeats after regular intervals of time. And here is one period, and here is half period, here is quarter period, here is 3/4 period. Like this it is going to be continued. The peak value is Vm. And we have learned in chapter electromagnetic induction, previous chapter, that Vm is equal to N BA omega. That is the peak value of voltage or voltage amplitude in the AC generator outputs. So this is the voltage time graph. Now going for current time graph. Current is also sine function, but its peak differs. So it may get another peak. That peak may be greater or lesser than the voltage peak. Peak may be voltage greater or lesser, but they are in phase. What do you mean by in phase? When voltage is maximum, current is also maximum. When voltage is 0, current is also 0. So phase angle is 0. Okay, now root mean square value of AC, Vrms, is also the DC equivalent. RMS value of that function, V is equal to Vm sin omega t, is the function. We have to find the root mean square value over the entire period, for which you can make use of this formula, 1 by t integral 0 to t v square dt within all square roots. So square root of 1 by t integral 0 to t v square dt. On carrying out that integral, we get Vrms as Vm divided by root 2. That implies 0.707 times Vm. That implies 70.7% of Vm. So root mean square value of voltage or current, Irms, similarly 70.7% of the peak current. Okay, and that is the steady value defined for the entire full cycle of AC voltage as well as current. Average value of AC over one cycle is 0, but root mean square value is chosen as the equivalent DC. Okay, by using this root mean square values, you can convert an AC equation into a DC equation and vice versa. For example, we have already learned Ohm's law, V is equal to IR. This is defined for DC situations. When you apply the same to AC situations, this voltage will be given a suffix root mean square. Vrms equal to IRMS into R. So average power, if you wish to get average values for DC like this, P equal to IV, then we may write average power is equal to IRMS times VRMS. So all DC equations we can convert into AC counterpart by using this root mean square value. RMS value is defined for AC. RMS value of AC is defined as the equivalent DC which produces same average power loss that AC does in same resistor under same conditions. Okay, so that is the definition of root mean square value. Now, phasors. What are phasors? Phasors are rotating vectors used for representing this time varying, periodically varying, either sine or cosine functions. Harmonic functions can be represented graphically by using phasors. Phasors are representing instantaneous values of voltages and currents by using straight lines with an arrowhead. Suppose this is representing the voltage phasor of AC through resistor only, then the current phasor also will be in the same direction because voltage and current are turning through a phase angle omega t in same time t seconds. In t seconds, voltage phasor as well as current phasor turns through angle omega t. So voltage is a phasor, current is also phasor, they are in phase. Now dropping a perpendicular from tip of each of these phasors, voltage phasor and current phasor onto vertical axis. Onto vertical axis, we get the corresponding vertical phasors. And this will be the opposite side where I is the current amplitude. Then this can be written Im sine omega t, which will be the instantaneous value. So for getting the instantaneous value of that phasor, we have to drop a perpendicular from the tip of that phasor onto the vertical axis and measure that projection. Similarly, you can measure the instantaneous value of voltage by finding the projection onto vertical axis, that is Vm sine omega t. That should be the instantaneous value. So projection from tip of any phasor onto vertical axis gives rise to the instantaneous value of the same. And phase angle between both the phasors in the diagram, graphical representation gives you the phase angle between the two. Here phase angle 0 because both are in same line, same phase. Okay. The defect with the phasor analysis is we may not know the initial conditions unless otherwise specified. Okay. For example, somehow we are watching voltage phasor and current phasor at an instant of time only we are watching it. That time voltage and current are seen to be in same phase. It is not necessarily always so. It may be that instant where voltage overtakes current, or it may be that instant when current overtakes voltage in a given situation. That we cannot say unless otherwise we may know the analytical method in solving this, or we may know it practically. So this phasor method alone cannot solve the entire problem unless otherwise it is defined initially. So initial conditions are to be well given. That is only drawback of phasor method. Phasor method is a most easy method in analyzing AC circuits. Okay, so AC through resistor. The only topic left is average power. Average power consumed by any AC circuit, you can use this formula: IRMS, VRMS, cos pi, where pi is the phase angle between the two phasors, where we can use this impedance triangle for defining that phase angle phi. Phi is the angle made by the resultant with the adjacent side. Okay, where the hypotenuse is defined as impedance Z, adjacent side resistance R, opposite side net reactance X. X is the net reactance of the circuit. Here, phase angle happens to be 0. That is why as phase angle is 0, tan 0 equal to 0. That is why X is equal to 0. That is why Z is equal to R. Always Z is equal to R for AC through resistor only circuit. And cos phi can be defined as R by Z. R is equal to Z. So cos phi is 1. Cos phi is called power factor. So what is the power factor of resistor only circuit? Power factor of resistor only circuit is 1. Phase angle is 0. Power factor equal to R by Z equal to 1. By heart the formula for power factor. So average power consumed by resistor only circuit, we can use this average power as IRMS into VRMS, because cos phi equal to 1. So average power equal to IRMS into VRMS. We can also define it in terms of the corresponding peak values. That's all about AC through resistor only circuits. Okay, what is the advantage of AC over DC? With AC, it is very easy to transmit with negligible power loss. AC when transmitted, normally transmitted at higher voltages to minimize power loss. It can be converted to higher voltage from the usual smaller voltage produced at the source by using transformers. So transformers work at the principle of electromagnetic induction, also mutual induction. This principle works whenever there is a flux change. Periodically, flux changes with AC because AC is a harmonic function. AC current or voltage harmonic function. That's why changes of instantaneous current and voltage are harmonically. That's why with the AC, a transformer can be used for stepping up or stepping down voltages. So you can use a higher potential difference for transmitting large power over large distances with negligible power losses. With the DC, power loss transmission will be large. Now, AC through inductor only circuit. Now it is easy to discuss the rest of the topic. AC through inductor only circuit. See students, this is only a quick revision. That's why I am not going for the entire theory. I am producing the results and discussing that. Inductor is a coil. When connected across the source as earlier, V equal to Vm sin omega t. Inductance L. Okay, usually in AC we do not give arrow marks because it changes periodically. From KVL, Kirchhoff's current law, the equation for current would be minus Im cos omega t. This minus sign indicates that current lags behind voltage. Voltage is sine function and current is cos function. It indicates that current is lagging behind voltage. Current is lagging behind due to this minus sign. Also, it tells that current is lagging behind. And one is sine and the other is cos. That phase angle is pi by 2. So, average power is equal to 0 because cos phi is equal to 0 because phi is equal to pi by 2. Okay, so in L only circuit, L only circuit, average power consumed is 0. This current can also be written as I as Im sin omega t minus pi by 2. It clearly tells you that the current is lagging in phase by pi by 2. So average power consumed 0 because phase angle is pi by 2. So that current is called wattless current. This current does not consume any power even when it is flowing through that coil. Current is flowing through the coil, but it doesn't consume any power. So inductor only circuit consumes no power. So that current through inductor which doesn't consume any power is called wattless current. So what is wattless current? Faultless current is the component of the current flowing through an AC circuit which doesn't consume any power. Okay. Now we have this formula, very important. With that, you must notice this also. Im is equal to Ohm's law, Vm divided by reactance, where XL is called inductive reactance. XL is equal to omega L, also can be written as XL is equal to 2 pi L, students. From this, you may be asked to find the reactance given, frequency given, you may be asked to find the inductance. Inductance and resistance are giving same units and dimensions. Resistance unit is ohm, so inductance also, reactance. Inductive reactance gets same units. Unit of inductance is different, that is Henry, that we have already discussed. Unit of inductance is Henry. Henry means joule per ampere square, Weber per ampere, all that we have discussed. Okay, Henry. Flux per ampere, Weber per ampere. Flux is volt second, magnetic flux. So volt second per ampere. So Henry, volt second per ampere, Weber per ampere, joule per ampere square, all these units of inductance. But inductive reactance is different, which is 2 pi f into L. That's very important. Okay, so inductance is the property due to which a coil has an ability to oppose any growth or decay of current. That also we have learned in chapter electromagnetic induction. So this KVL equations and also this phase angle, current is lagging behind voltage, that also important. XL equal to L omega, inductive reactance, all this important. Average power consumed is 0. Now the phasor diagram. Phasor diagram, how? Here voltage is leading. Voltage across the inductor is leading. That's why I can show like this. Current through inductor is lagging by phase angle pi by 2. Okay, when voltage phasor turns through an angle omega t in time t seconds. Okay, then current phasor also turns same angle, but they are not in phase, dropping onto vertical axis. You will measure projection for voltage phasor as Vm sin omega t, that is the supplied voltage, and the output is, which is the current available, that is the circuit current, minus Im cos omega t, because it is adjacent side and that is the negative side, that's why it is minus. So you can choose such a diagram clearly to mention the phase relationship between voltage and current, which tells you phase angle is pi by 2. Okay, now you can draw the voltage, hence current graphs made with vertical, horizontal. Vertical is voltage or current, horizontal is time. Okay, let us draw voltage graph. Voltage graph will look same as we have drawn before. That would be this one. Okay, the peaks not necessarily same, that's all. Sometimes peaks are also same. Okay, this is a voltage graph. Now, what about the current graph? Current minus cos omega t, so it should be a negative cosine curve. So it should be negative cosine. So when voltage is 0, current is maximum. When voltage is 0, current is maximum, and when voltage is maximum, current is 0. That's why you have to choose such a graph. You have to choose such a graph. You see this graph like this. Graph is chosen as I have drawn here. So the phase angle between the two is pi by 2 and current is lagging. So at t equal to 0, t is on horizontal axis. At t equal to 0, current is behind. So this side, it can be either voltage or current. So this is the voltage current relationship graph, and this is the phasor diagram. Now AC through capacitor only circuits. AC through capacitor only circuit. AC circuit having only capacitor. Supply voltage is V equals Vm sin omega t. Capacitance C. Then circuit current is equal to Im cos omega t from KVL equations. That is I is equal to Im into sin omega t plus pi by 2. Then graph showing the variation of voltage with time and current with time. Voltage with time and current with time, as we have done earlier for inductor only circuit. Okay, voltage variation. Voltage variation. Voltage variation. Like this. Variation of voltage with the time. Variation of voltage with the time. Now variation of current with the time. Current leads voltage by phase angle. Current leads voltage by phase angle pi by 2. Current is leading. So where voltage is maximum, current is 0, and where voltage is 0, current is maximum. Where voltage is maximum, current is 0. Where voltage is 0, current is maximum, so and so. So it continues like this. So voltage time as well as current time. And this will be voltage time, and this one is current time. So voltage or current on y-axis and time on x-axis. Now phasor diagram. The suited phase diagram here. First we draw voltage across capacitor. Voltage across capacitor. And current is leading. Then current is leading by a phase angle pi by 2. So this angle is pi by 2. In t seconds, voltage phasor turns through an angle omega t. Okay. At that instant, current phasor is at an angle omega t plus 90 with respect to x-axis. This is current phasor dropping a perpendicular onto vertical axis. From each of the phasor's tips will give you instantaneous values of voltages and current. This value is Vm sin omega t, and this length will be given by Im cos omega t. That are instantaneous values as we have plotted it earlier. As it is a mere repetition, it will be feeling comfortable for you. So that is AC through capacitor only. Now, what is Im? Im is equal to Vm divided by XC, where XC is the capacitive reactance, where capacitive reactance is given by 1 by C omega. XC can also be written as 1 by 2 pi Fc. So that voltage across voltage across capacitor is equal to current through capacitor into the capacitive reactance. All these equations are important. Okay, this reactance is XC. Reciprocal of reactance is called susceptance. Reactance, inductive or capacitive, both are having same units and dimensions. Inductance has unit Henry. Henry means joule per ampere square, or Weber per ampere, or volt second per ampere, or Henry. All these units and dimensions we have already discussed. Inductance is a scalar. Okay, now what is the unit of capacitance? Unit of capacitance is farad. Unit of capacitive reactance is ohm, same as that of inductive reactance. Reciprocal of reactance is called susceptance. So capacitor only circuit, current, reactance, all these topics important. Capacitive reactance is not a constant, it varies with frequency. At high frequency, capacitance offer less reactance. That is why it is called a high pass filter. Capacitor is used as a filter in AC circuits, and it is called a high pass filter. At the same time, an inductor is called a low pass filter because inductive reactance is proportional to the frequency. Capacitive reactance is inversely proportional to the frequency. As you increase the frequency of the supplied AC in capacitor only circuit, what happens? Students listen, as you increase the frequency of the AC supply to the capacitor only circuit, capacitive reactance decreases, thereby increasing current. Current is equal to Vm by Xc. So that current maximum amplitude of current Im can be written as Vm divided by Xc. But Xc equal to 1 by c omega. So that Im equal to Vm c omega. So when you increase frequency alone, keeping amplitude of voltage and capacitance a constant, you increasing frequency of the supplied voltage alone, you will get increasing current. Im directly varies with omega. That's why it is called a high pass filter. Capacitor is used as a filter circuit. Now, average power consumed by this capacitor only circuit is again 0, and the current is wattless current, as we have discussed in inductor only circuit. So the current is called wattless current. The component of the current which does not consume any current in AC, any power in AC circuit is called wattless current. So average power is 0 because cos phi is equal to 0, because phi is equal to pi by 2. Cos phi is called power factor. So power factor of capacitor only circuit is 0, as power factor of inductor only circuit is also 0. So power factor of capacitor only and power factor of inductor only circuits are both 0. So average power consumed by capacitor only circuit. Phasor diagram. Voltage and current versus time graph. Supply voltage Vm sin omega t, circuit current Im cos omega t, Im sin omega t plus pi by 2. Current leads by a phase angle pi by 2. Students, so by head and make it fluent. Phase angle between voltage and current is pi by 2. Capacitor is called a high pass filter for AC circuits. It is used as a high pass filter. It permits high frequency AC better than low frequency one. Current is leading by phase angle pi by 2. Okay. Now we are combining this inductor, capacitor and resistor all in series. That is in our syllabus. Series LCR circuit. LCR series circuit. LCR series. L means inductance, C means capacitance, R means resistance. Then supply voltage is still same, V equals Vm sin omega t. L inductance, C capacitance, R resistance. Okay. Here the circuit current may be I is equal to Im sin omega t plus or minus phi, where phi is the phase angle. Let us go for finding the phase angle by drawing the phasor diagram. The phasor diagram of circuit. First we draw voltage across a resistor, then voltage, now current through resistor. We know voltage across resistor and current through resistor are in phase. There is no phase angle between voltage and current in resistor. In resistor, when voltage becomes maximum, current is also maximum. But in inductor, it is not so. In inductor, when voltage becomes maximum, current is 0. So there is a phase angle pi by 2. So we cannot draw current and voltage for inductor in phase. You have to choose 90 degree out of phase. There also, you know, in inductor, voltage is leading. Care should be taken while drawing inductor voltage. That can be drawn here. Voltage across inductor. Voltage across inductor. Okay, that can be drawn here also. Okay. Now, voltage across capacitor. Voltage across capacitor can be drawn here. Voltage across capacitor. So this is voltage across inductor, voltage across capacitor. What is the phase angle between voltages across inductor and capacitor? 180. What is the phase angle between voltages across inductor and resistor? 90. Inductor voltage leads. What is the phase angle between voltages across resistor and capacitor? 90. Which one leads? Voltage across resistor leads. What is the phase angle between current and voltage across capacitor? Pi by 2. Which is leading? Capacitor current. Voltage across inductor and current, phase angle 90. You can see that phase angles you can directly read from this diagram. So this diagram is very important. Okay. Also, VL and VC are 180 degree out of phase. So we have to subtract VL and VC. Suppose that VL is greater than VC. VL is greater than VC for this picture. That's why the difference would be VL is greater than VC. So let me draw that little more longer. So VL is greater than VC. So the difference would be along upward, and that is called VL minus VC. Then draw the third closing side. The third closing side, keeping VR as adjacent side, VL minus VC are opposite side. The third closing side will give the supply voltage or the resultant. So AC voltage supplied is V. Phase angle between the supplied voltage V and circuit current I is phi. That is nothing but the phi mentioned here. In T seconds, supply voltage turns through an angle omega t. At the same time, in T seconds, voltage across a resistor and hence current in the circuit, current in the series circuit turns at an angle omega t minus phi. Omega t minus phi. So what is the phase angle between voltage and current? Phi. Current turns through an angle omega t minus phi. Okay, voltage turns through an angle omega t in T seconds, current turns through an angle omega t minus phi, current is lagging, then VL is greater than VC. When VL is greater than VC, only current is lagging. So this is series LCR circuit. Okay, is it clear? Series LCR circuit phasor diagram. So circuit current can be plus or minus. Here I have chosen minus. That's why this equation would be I is equal to Im sin omega t minus phi. Dropping a perpendicular from tip of the current phasor onto vertical axis and measuring that length. This length you can measure. This length you can measure as Im sin omega t minus phi, and that is the instantaneous current through the series LCR circuit. Okay, hope that you are clear. Now, the total obstruction offered by series LCR circuit to the flow of AC is called impedance. Impedance has its reciprocal called admittance. Impedance, acceptance, resistance all are having same dimensions. Therefore, current amplitude is equal to voltage amplitude divided by Z in AC circuit. RMS value of current is equal to RMS value of voltage divided by impedance, where Z stands for impedance. Impedance is the total obstruction offered by series LCR circuit or any AC circuit to the AC. So impedance has its unit ohm, reciprocal, admittance. Okay, so IRMS equal to VRMS by Z. So the general formula for average power also you can use here, IRMS, VRMS, cos phi, or IRMS, VRMS into cos phi is R by Z. IRMS can be written as VRMS divided by Z. IRMS equal to VRMS by Z. Then you get VRMS square divided by Z. Cos phi is R by Z. That is average power. You can have this equation, very popular and important equation. Many times it is asked for exams. VRMS square into R by Z square. I heard that also, average power. Here, voltage across inductor is greater. But if voltage across capacitor was greater, this arrow mark would have been drawn downward, and there the phase angle for current would have been omega t plus phi. So this answer would have been Im sin omega t plus phi. Okay, so current may lead or current may sometimes lag with respect to voltage. Okay, right? Now, what's impedance as well as what is an impedance triangle? You draw an impedance triangle where this angle between the resultant voltage and resistance, you change the sides, voltage across resistance, this V you change as Z, voltage across resistor you change as R, voltage across reactance you change as net reactance. Net reactance is X, where X can be XL minus XC or sometimes XC minus XL, whatever its numerical value. Okay, so this triangle you can find out tan phi. tan phi equal to XL minus XC divided by R. Then sin phi equal to XL minus XC by Z. Then cos phi, where is power factor, which is equal to R divided by Z. So here cot phi, cosec phi, secant phi, all that you can define from this. So this is the triangle which is called impedance triangle. For example, if in such a case where the resistance is equal to reactance, it means that phase angle is 45. That whole idea will be clear here. If resistance is reactance is 5 root 3 and resistance is 5, then 5 root 3 by 5 is root 3. So tan phi equal to root 3, phi equal to 60. That type of questions you can quickly answer if you have an awareness of this impedance triangle, right? So impedance triangle is very important topic. Therefore, the circuit current has its amplitude. Current amplitude is equal to voltage amplitude divided by impedance. Where from this triangle you can write impedance as square root of R square plus XL minus XC the whole square. That's very important statement. That's why the current amplitude is given by Vm divided by square root of R square plus omega L minus 1 by omega C the whole square. Now you draw a graph showing the variation of the peak current amplitude Im, which is on y-axis in ampere, and angular frequency of the supplied AC voltage omega on x-axis. Okay, you try keeping Vm, voltage amplitude is a constant. So when omega increases from a very small value continuously, when omega increases, you'll come to know that the denominator decreases and becomes minimum when omega L is equal to 1 by omega C. Denominator becomes minimum. Denominator is impedance. Impedance becomes minimum when omega L equal to 1 by omega C, that is omega square is 1 by LC, that is omega is 1 by root LC, or frequency as 1 by 2 pi root LC, omega by 2 pi, or time period as 2 pi root LC, that phenomenon where the current amplitude has become maximum, that is called resonance. So the current amplitude has become maximum. Im maximum is equal to Vm divided by R. So Im max is equal to Vm by R. What is Im max? Im max is the current amplitude maximum. Maximum of the current amplitude is called Im maximum. And Im maximum is equal to Vm by R. Okay, omega L equal to 1 by omega C is the condition for resonance. Z is minimum. Omega is 1 by root LC. All this very important. At resonance, impedance becomes minimum. So as you continuously increase omega, what happens when omega increases? Denominator decreases, becomes minimum. That means impedance decreases, becomes minimum. Then current increases and becomes maximum. Current increases and becomes maximum. Then current goes to be decreasing. And first current increases, becomes maximum, then decreases. That phenomenon is called resonance. The current amplitude is now its maximum, Im max, where it is omega 0. So when omega has that characteristic value, current is maximum, that called at resonance. Omega we notify omega 0. So at resonant angular frequency omega 0, which is nothing but 1 by root LC, frequency f0, time period t0, all that we can denote by using that suffix 0 or something else. Okay, omega 0 is called resonant angular frequency. If frequency supplied AC is less than or greater than omega 0 to the left of that peak, then the circuit is inductive or capacitive. That is capacitive. And when omega is greater than omega 0, the circuit is inductive. So when omega is less than omega 0, circuit is capacitive. Omega greater than omega 0, circuit is inductive. So at higher frequency circuit is inductive and lower frequency circuit is capacitive. Higher frequencies capacitor drop voltage drop across inductor will be larger because of L di by dt. Di by dt is large at higher frequencies. Okay, so when omega is greater than omega 0, circuit is inductive. Omega less than omega 0, capacitor circuit has capacitor nature. When circuit is capacitor, current is leading. When circuit is inductive, voltage is leading. So when voltage leads, when supply voltage has frequency greater than the resonant angular frequency omega 0. Okay. Now you choose a current which is equal to 70% of the maximum current. Im max divided by root 2. I have chosen a current Im as Im max by root 2. Then I got two frequencies here. These two frequencies due to symmetry are equally on either side of the resonant frequency. Let this be called omega 2. Let this be called omega 1. And this change, a small change called delta omega. So due to symmetry, this is also delta omega. Okay. This line, this horizontal line which is passing through the 70% of the maximum current means Im max by root 2 splits this graph into two symmetric portions. Okay. Where omega 1 can be written as omega 0 plus delta omega. Omega 2 can be written as omega 0 minus delta omega. Therefore, omega 1 minus omega 2 is 2 delta omega. That is called bandwidth. So, what is the bandwidth of series LCR circuit? Bandwidth is the operating range or range of frequencies over which the current is 70% of the maximum current. Maximum current in the 70% current varuna frequency omega 1 to omega 2. That frequencies are called half power frequencies. Difference of half power frequencies is called bandwidth. Okay. From this we will define Q factor and we will discuss rest of the equations. Okay, without any proof, because it is a quick revision, we have no time to deduce all that. Okay, then Im max is equal to, all formula I will write. Im max is equal to Vm by R. Also we have chosen Im as Im max divided by root 2 when omega equal to omega 1 and omega equal to omega 2. There are two frequencies called omega 1 and omega 2 are half power frequencies. Omega 1 and omega 2 are half power frequencies. So what do you mean by half power frequencies? Omega 1 and omega 2. So Im is equal to Im max divided by root 2. Im max is equal to Vm divided by R. All this important. Okay. That you can choose here, that Im max can be Vm by R. That implies Im as Vm divided by R root 2. But Im can be Vm divided by Z. Im equal to Vm by Z. That's why Z is equal to R root 2. Z is equal to R root. So Z is equal to R root 2 here. For half power frequencies, Z by R is equal to root 2. So R by Z equal to 1 by root 2. R by Z is power factor. So power factor is equal to cos phi equal to 1 by root 2. So that phi as 45 degree. So what is the phase angle between supply voltage and circuit current? What is the phase angle between supply voltage and circuit current? For half power frequencies, phase angle is 45 degree. That's very important. Okay. And at resonance, what is the phase angle? At resonance, we know impedance is minimum and that is equal to R. So cos phi equal to R by Z equal to 1. That is power factor is unity for resonance. That is phi as 0. So at resonance phase angle is 0. So you see this graph. As you move here along this line, when you reach here the phase angle is 45. As you move up to here, phase angle becomes 0. Here to here, phase angle again increases and becoming 45. So phase angle decreases, becomes minimum, then increases. Current becomes maximum, decreases. Impedance decreases, becomes minimum, then increases. All this type of statement type questions may be asked. Okay. So at resonance, phase angle is unity, power factor is 1, maximum power is consumed at resonance. Okay. Now, Q factor is defined as omega 0 L divided by R, where omega 0 L is the value of inductive reactance at resonance. So, inductive reactance at resonance by R. That is why it can be written as voltage across inductor at resonance divided by voltage across resistor. Voltage across inductor equal to voltage across capacitor at resonance. That is why VC at resonance divided by VR. So VC at resonance by VR. Okay. XL at resonance can be XC at resonance. So XC at resonance divided by R. What is XC at resonance? That is 1 by omega 0 C. So Q factor have a very important formula, 1 by omega 0 CR or omega 0 L by R. One more formula substituting for omega 0. Omega 0 is what? 1 by root LC. You get one more formula, 1 by R root of L by C. It's most popular formula. This is also to be by hearted. Many formula for Q factor. By heart all this. Try to write it down and practice. Okay, you should be fluent enough to answer this. Q equal to 1 by R root L by C. Q factor varies inversely with resistance. When resistance increases, Q factor decreases. When resistance increases, Q factor decreases. A Q factor determines the sharpness of resonance. Then the resonance circuit becomes more selective. You can easily select out of ranges of values. You can easily select. Okay, if Q factor is maximum, sharpness is maximum, resonance has got its maximum sharpness, but circuit has more resistive properties, Q factor is less, so sharpness is less. So that resistive element of this LCR circuit should be minimum to get maximum Q factor. Okay, so what is the bandwidth? Bandwidth is equal to omega 0 divided by Q factor, or Q factor is equal to omega 0 divided by bandwidth. Another formula for Q factor. Q factor you can also get omega 0 divided by 2 delta omega. So that delta omega equal to omega 0 divided by 2Q. Okay. Now omega 1, as I have written earlier, you just take that page, take a screenshot and compare and try to write it. Omega 0 plus or minus delta omega. Omega 1 I have written omega 0 minus delta omega, and omega 2 I have written omega 0 plus delta omega. Anyway, this omega 1 or omega 2 that may be written as plus or minus, right? Omega 1 or omega 2 either. Okay, plus or whatever name you can choose. Anyway, omega 0 plus or minus omega delta omega. That is omega 0 plus or minus. What is delta omega? Omega 0 by 2Q. That is omega 0 into 1 plus or minus 1 by 2Q is the formula for one of the half power frequencies is with the plus, other one is with minus. The difference of half power frequencies will give you the bandwidth. Difference of half power frequency is equal to the bandwidth. Okay, bandwidth is very important topic. Okay, so bandwidth, sharpness of resonance, resonance in series LCR circuit, all these finds of great importance. Okay, so series LCR circuit including resonance we have discussed. Now we have to continue with the LC oscillations for revision. LC oscillations. After that we will move on to transformers. LC oscillations. A capacitor is being charged by using a battery of EMF V. Capacitance is C. Okay, then battery disconnected. then one of the pole is positive, other is negative, connected through an inductor L. The energy stored in the capacitor start to discharge, and that energy in the form of electrostatic potential energy in capacitor comes in the form of magnetic potential energy in inductor. Then energy in capacitor is half C V square, and the maximum energy, suppose the EMF is V0, maximum energy half C V0 square, that is converted into half L I0 square, where half L I0 square is the maximum energy in the inductor. Okay, that is half gets cancelled. I0 equal to C divided by L into V0 square. I0 square. So I0 equal to square root of C by L. I0 equal to square root of C by L into V0. In that way, we can find out a relation between I0 and V0 during LC oscillations. Such back and forth oscillation of electric energy as well as magnetic energy in the circuit is called LC oscillations. Okay, the capacitor is getting fully charged at the time when it is starting to discharge during the transients. The current I in the circuit can be defined as minus dq by dt. Initially charge is maximum, so that can be q0 cos omega t. We are assuming there is no initial phase. So current I as q0 omega sin omega t, you take the first derivative. So I equal to I0 sin omega t, where I0 is equal to q0 omega. So it's very important topic that I0 by q0 as omega. Current amplitude by charge amplitude is omega. Ratio of maximum current and maximum charge is called the frequency of LC oscillations. Okay, so frequency of LC oscillations can be measured as I0 by q0. Okay, now the voltage across inductor is L di by dt. Voltage across capacitor is Q by C. I is minus dq by dt. Okay, then this voltage is also minus L di by dt. So minus L di by dt plus Q by C equal to 0, we can write like this, so that L into d by dt of I is minus dq by dt plus Q by C equal to 0, minus of, and this minus of minus become plus. That is why L d square Q by dt square, L d square Q by dt square plus Q by LC equal to 0. That is d square Q divided by dt square plus Q by LC. L I have already removed from here. L I have brought down. Q by LC. D square Q by dt square plus 1 by LC times Q. 1 by LC times Q is equal to 0. This you can compare with the differential equation for simple harmonic motion. So that omega square is equal to 1 by LC and omega as 1 by root LC. That is the resonant frequency equation looks like, but doesn't have any connection. And this is called the angular frequency of LC oscillations, omega 1 by root LC. So frequency F is equal to 1 by 2 pi root LC. F is equal to omega by 2 pi. So 1 by 2 pi root LC is the formula for frequency. Frequency proportional 1 by root L. Frequency proportional 1 by root C. Very important. Time period of LC oscillations is 2 pi root LC. Okay, so LC oscillations refers to the back and forth oscillations of energy in inductor and capacitor, or it can be termed as the oscillation of charge in the plates of the capacitor. It can be termed as the oscillation of current in the circuit. Charge in the circuit oscillates simple harmonically. Current in the circuit simple harmonically oscillates. But energy of the circuit oscillates only harmonically, not simple harmonically. If frequency of oscillation of the charge is N, frequency of oscillation of the current is also N, then frequency of oscillation of energy is 2N. Because half L I square, it will be second order, like sine square, second power, sine square or cos square. That's why the frequency with which energy oscillates back and forth during LC oscillation is not simple harmonic, but it is only periodic or harmonic with double the frequency of current and charge. All this data very important. Okay. At any instant, the energy of capacitor plus energy of inductor will give rise to the maximum energy. So energy conservation is not violated in this process. During LC oscillations, the amplitude is gradually decreasing. So it is a damped oscillation. Damped oscillations can be LC oscillations for small amplitude. So I0, V0 values may be less, for which it can be remaining simple harmonic. Okay. Now transformers. The last topic of the chapter, transformer. Transformer, device used for converting higher potential AC voltage into lower potential AC voltage, or lower potential AC voltage into higher potential AC voltage. So AC voltage or current can be stepped up or stepped down. For step up transformers, the usual symbol, step up transformers, usual symbol looks like this. Step up transformer have got two turns. One is called primary and the other is called secondary. Step up, for which voltage is to be stepped up. So primary will have turns, number of turns less and thicker coils used. Secondary, number of turns much more and turns are thinner. It operates only with AC, both input and output AC. Primary, secondary. Number of turns in primary NP, number of turns in secondary NS. Voltage in primary VP and that in secondary VS. Then power in primary PP, power in secondary PS. Current in primary IP, current in secondary IS. For an ideal transformer, ideal transformer, power in primary equal to power in secondary. Ideal transformer means there is no loss in energy. There are mainly four types of losses of energies in transformers. Mainly we have discussed in last chapter. One is Joule loss, second one is hysteresis loss, third one is flux leakage loss, fourth one is eddy loss. Okay, if there is no such losses, input and output powers are same, so 100% efficiency. Then power in primary can be current in primary into voltage in primary. Power in secondary can be current in secondary into voltage in secondary. That is why IP by IS is equal to VS by VP. Also you can have an extension which is equal to NS by NP, which is called the turns ratio of the transformer. But if the transformer is not an ideal one, which is a real transformer whose efficiency is less than 100%, then you can use efficiency as output power divided by input power. So efficiency as IS VS divided by IPVP. Efficiency may be mentioned in percentage, maybe 90% or 80%. Then that is equal to IS VS by IPVP together with this turns ratio. Okay. Transformer only works with AC. There are mainly four energy losses in a transformer. The advantage of transformer is it can be used for stepping up and stepping down voltages and currents. It never amplifies. It's not acting as an amplifier. Okay, but there is a phase angle between input and output. Output is 180° out of phase with the input. If input graph is a sine curve, output will be an inverted sine curve. Okay, if it is a stepped up one, voltage amplitude is much larger. Okay, stepped up. Voltage when stepped up, current is stepped down. A step up transformer refers to increased voltage but decreased current. A step down transformer refers to decreased voltage but increased current. So when current increases, voltage decreases. In primary, for transformers which are step up transformers, I have shown only step up transformer. Step up transformer, secondary has more resistance as there are more number of turns and thinner one. When thickness decreases, resistance increases. Number increases, resistance increases. So secondary resistance is much larger than that of primary. That's why current in secondary has been reduced considerably to keep power a constant. Voltage has been increased, and this can be used for transferring power transmitting power over long distances without much ohmic loss. Power transmission is done at higher voltages. That's why step-up transformers are used for increasing the voltage so that the power is transmitted effectively, affordably. Okay, with that we stop the quick revision program of the chapter alternating current. Soon we will be meeting with the next chapter, electromagnetic waves. Thank you.